How do you do, ladies and gentlemen, and boys and girls, and mothers and fathers, and everybody? I'm Julius Sumner Miller, and physics is my business. And today, a strange kind of physics for an old man, an old physicist. The physics of toys. I don't suppose there is another physicist in all of history, dead or alive, who has played with them so abundantly as I, for the purpose of understanding why it is that it works. I am reminded that the great James Clerk Maxwell, when a little boy, was given to the phrase, "What's the go of it?" Meaning, in my phrase, why is it so? Why does it do what it does? Or as Kepler used to say, why things are as they are and not otherwise. So I'm going to entertain us with some explorations into the physics of toys. I have characterized toys as mechanical toys, acoustic toys, thermal toys, magnetic toys, electrostatic toys, electric toys. I don't have any nuclear toys, but maybe in due course. So let's look at some at random. It does not matter what the order, but here is a mechanical toy which is very enchanting. I have here a little dog, which you recognize as Pluto. His legs are free in the plane of his long front to rear axis. And I have a string attached to his nose, and to the end of the string some weights, paper clips. Now I put him on the table with the string hanging over and the paper weights hanging freely, and I'm going to put him into motion. Watch now. There he goes. Now I'm going to stop him because there is something to say. Does not reason suggest that when he gets to the end of the table, he should fall off, be pulled over? That is what reason suggests. But I'm going to show you this is not what a physicist expects, nor indeed is this what will happen. Watch it now. Watch it. Oh, notice a little too much friction there. I'll start him again. Watch him. No, he didn't fall over. And now I'm going to remark about the physics. Here in the horizontal, the pull was horizontal. So a horizontal pull can produce horizontal motion. Now when he gets to the very edge, I hope you see that the pull is vertical. And a vertical pull has, as we say in physics, no component in the horizontal, so he cannot move further. Indeed, here is a pair of firemen, identically equipped, and watch. One would think that they would fall over. No, they didn't fall over. And I am reminded, doing a program on the physics of toys in Oslo, Norway, I decided to have a wager with the professor who is playing the game with me, and so we will race these two. Watch it. Watch it. Oh, Disney would be delighted that his Pluto won the race. There we are. So, what am I led here to say, here and now? The competence of children is shamefully underrated. I could teach the physics of this to 4-year-olds, indeed 2.5-year-olds. I gave a lecture to about 100 pre-kindergarten, kindergarten children in Australia last year. Very exciting they were. All right, next demonstration. Next demonstration. I have a little toy car with a smokestack and wheels, and I'm going to turn a screw thing here. What am I doing? I am winding up a spring. I am storing some elastic energy in a wound-up spring. Then when I release the spring unwinds, turns a fan, blows a stream of air out of this smokestack. Watch it. Now I'm going to show you something very dramatic. Why does the ball stay there? Well, everybody says, Professor, there's nothing to that. The stream of air coming out of that stack is vertically up. The air pushes up, the ball pushes down. When they are equal, the ball stays there. And that would be right. But now supposing I turn that smokestack off the vertical and the ball still stays there. Aha, we got a new piece of business, and that ain't so easy to understand. Somebody says, well, Professor, that ain't so easy. That's not good English. Well, I take liberty and license with the language. Notice, liberty and license with the language. That's very good alliteration. Watch this now. Watch it. And the ball is spinning. And the ball is spinning. Of course, too much off the vertical, fall down. And I want to know why it does that. Oh, this would take me about an hour of blackboard mathematics to show you why. But let me say this. Why the ball stays there in this position, spinning in a very interesting way, which you witnessed, is quite answers or lies in the same category as the following. Why I can throw a baseball in a curve, why an airplane can fly, why a smokestack has a good draft, why a bird can soar in the air, why a flag can flutter, and 1,000 such things. So you see the physics in this toy car is not trivial. Not trivial. Consider the following. Notice, these are mechanical toys. Here is a little propeller, and it has 3 blades, and they are pitched in a very certain way. Now I have wound up, oh, that one is wound. Let me take, there. Whoop. What am I doing? Oh, there's a little trouble with that spring. I have stored some twist energy in a spring. When I release it, it will unwind, and that propeller is going to go up. Why? The blade is pitched. So as the whole wheel turns, the blade grabs some air, as we would say, and pushes the air down, and that's why it goes up. So a bird can fly only because he pushes the air down and he goes up. Conservation of momentum, we call it. Watch it. There it is. And of course, there I have a spinning top, which I could talk about for an hour. Let me do another one. Oh, watch it now. Watch it. Oh, way up, and there it comes. And we have a spinning top on the floor, which perhaps can be caught by the camera, and that's so. Very good, men. Okay, mechanical toys. Another one. Here is a wonderful one. I don't like to play much with weapons of war, so you have once detected my philosophy, but this is rather harmless. Here is a hollow chamber in the shape of a gun. The chamber is, as one would say now, empty. Oh, no, it's filled with air, And here is a ping pong ball, and I put the ball in there, and now I squeeze suddenly on here, and the ball emerges. Indeed, I have made a very profound experiment out of this. If I shoot this ball at some angle with the horizontal, and then at another angle with the horizontal, and then at another angle with the horizontal, I find very nearly the following, and this is quite amazing. If one shot a projectile like that and it took this flight, the question is, when would you expect maximum range? Well, theoretically, maximum range is at 45 degrees. And so we can show that with this toy. Now, there is another interesting problem. Galileo showed that if there is a target intermediate in here somewhere, that target can be hit by this weapon by 2 routes. One that goes like this, and one that goes like this. And they have very interesting properties. This smaller one is as much smaller than 45 degrees as this one is bigger than 45, which is a very exciting thing. And Galileo did this in the 16th century. So you see, people, that playing with a toy, this may be for child's play, but the physics ceases to be child's play. It can be very substantial business. Let me show you another one. Here I have my monocyclist. Mono, one, cycle, wheel. monocyclist. Here I have a string, one end of which is fixed to a support there. Now you know that if I put this monocyclist on the string, the center of gravity of the cyclist is far above the point of support, whereupon, as we say, the system is unstable. Unstable. Very certainly will tip. I wish to do two things. I want to make him more stable. How can I do that? I can do that as follows. I can load his arms with a stick and a heavy weight. Here's the weight, a lead weight. Put such in each arm. Notice I'm getting a little entangled here. Put one in each arm. I'll go get my string again. And now let me discuss the physics briefly. Mark you people, I am giving only the most superficial inquiry into the matter. Each one of these toys could have 100 pages of mathematical physics written on it. So I am disposing of it quite in a trivial way. What have I done? I have lowered his center of gravity below the point of support, and I have also increased what we call his moment of inertia. I have made his mass far out from his central axis, and now we hope he can ride with absolute immunity. Watch him. There he goes, and there he comes back, and there he goes, and there he comes back. And the faster he goes, the more stable, which is because the wheel has a certain gyroscopic property, which I have no time to engage in here. So the monocyclist lowered the center of gravity below the point of support and increased the moment of inertia. Let me say a word more about that. Supposing I'm an ice skater, skating, and I stop with one leg up and both arms out, and I spin at a certain speed, pirouetting. My mass is far distributed from my axis of rotation. Now I drop my arms. My moment of inertia becomes less, and my angular velocity very much more. Or consider finally another. Here is a little dog with a flexible neck, and I push his nose down into some stickum stuff. I push his nose down. Watch now. Watch. Watch it. Watch him. Come on, come on, come on. Oh, come on, you rascal. He stuck him too much. Oh, well, notice, what I wanted to show you is that he rotates about his center of gravity and would land on his feet. And thus I have explored in a trivial way the wonderful adventures in the physics of toys. And I thank you for watching.